asking you. Priya, my voice is clear? Okay. So let me present my screen to you all. My screen is visible. Hello. My screen is visible.
Yes, ma'am.
Okay. So listen, everyone. Today, see, in your class, I have explained Algama crypto system, right? So all of you know that for Algama crypto system, see, first of all, let me check how many students are there. Let wait for 1 or 2 minutes for others to join. Okay, and then I will start a live session. Okay, so wait for 1 or 2 minutes. I think, see, all of you know the concept of Algama crypto system already that I have explained in your class, right? So, somewhat brief introduction I will give you what you have to do in today's lab. Okay, and then after we will start our lab. See, too many students are joining late, so please make sure that next time be on time, everyone. Again, wait for 2 minutes for others to join. Okay, so let's start with our session. Okay, so listen, in your lecture, I have explained you the system. So today, what is your task? All of you know that, see, first of all, I will show you that algorithm system, and just wait. See, this is your Algama crypto system that I have explained, and all of you know that in Algama crypto system, you require primitive root, right? Primitive root. So first of all, today's your task is first of all you have to find the primitive roots, and once you find the primitive roots, then after you have to for Algama crypto system, first you have to perform key generation, then after encryption, and then after decryption. So this is the flow of your today's life. Again, I repeat everyone. First of all, because for Algama crypto system, you have to find the primitive roots. So first of all, the primitive roots that you have to find. Once you get the primitive roots, then after for Algama crypto system, first you have to perform key generation, then after encryption, and then after decryption. So this is the flow of your today's lab, right? Now, how to find the primitive roots? So that I have explained in your class also. See, one of the method that is using this, all of you see, today I will not explain that thing because already that I have explained you in your class by using cyclic subgroup, right? So this method, this cyclic subgroup that I have explained in your class, and based on that you can find the generator, right? So that is the one approach that is based on that you can find the primitive roots. So that one approach that I have explained in your class. Now then another approach, which approach that I have explained in your class, that is you have to compute the table by using a raised to I mod n. Okay, so now see, let's just see here the example. Just wait. Okay, first of all, can anyone tell me what is Z10 star? Z10 star means? Please reply in the chat window, everyone. Z10 star means? Hello? What is the meaning of Z10 star? Hello? Yes. So which elements are there, Priyank, in Z10 star? Which elements are there in Z10 star? Please reply in the chat window, everyone. 1379. Yes, correct, everyone. Right? Sorry. So, listen, here what you have to do. So, if you want to find the primitive root, so first of all, you have to compute the table by using which formula a raised to I mod n. So now see this concept that I have explained in your class. So 1 raised to 1 mod n, that means what you are getting 1, 1 raised to 2 mod n, then what you are getting 1, right? Similarly, you have to compute this. And see, here you can say, sorry. Sorry, everyone. See here, what four elements are there, right? So up to here you can see that how many elements are there? Four elements are there. So you have to start from here. Again, you have to compute 3 raised to 1 mod n. So that means mod n, so that means 10. So 3 raised to 1 mod 10, what you get 3. 3 raised to 2 mod 10, what you get 9. Right? 3 raised to 3 mod 10, what you get 7. 3 raised to 4 mod 10, what you get 1. Right? So in this way, listen, in this way you have to compute a raised to I mod n. Okay, so now here you can say that every time how to find the primitive root. So you have to check which condition. So you have to check a raised to my I mod n, that is equals to 1, as well as you have to check that where in which position you get 1 when the I equals to n minus 1. Because see here when you observe here in this case, or in this case here you have to check the condition. So here, see here also you are getting 1. Here in this position also you are getting 1. But here you have to check the condition. Here 3 and 7 are primitive roots. So you have to use this formula a raised to I mod n, and then you have to check a raised to I mod n equals to 1. At the same time, also you have to check that I should be what? I should be right now. How many the elements, total number of elements is that is n. So n is 4. So I should be n minus 1. Okay. So in this position, I should. So total here you can say that if it is in at last in last position if you are getting one, that you have to check, as well as you have to check a raised to I mode and that is equals to one, and at the same time also you have to check which condition at last you get one. So then you can say that that elements are primitive root. Okay, so in this way you have to write the logic, everyone, because see, when you observe that in this case a raised to I mode and also here I am getting one, but at that time it is not at last you see here in this case see you have to check that at last if it is one, right, that condition also you have to add, because so there you can say that it's a primitive root. Okay, so because in middle one also you are getting, so see if in some case if in middle you are getting one, right, so at that time you have to break the loop. Okay, so always you have to check, everyone, the a raised to I mod n that is equals to 1 at that also at last you should get 1, right? So then that becomes your primitive root. In between if you are getting at 1, so at that time you have to break the loop. So up to this clear, everyone, in which way you have to think for logic? Is it clear to you all what I'm trying to say? Hello? Please reply in the chat window so I can understand. Hello? Can anyone speaking? See here. Priyank, I think by you seeing this, you can is it clear to you all? Z7 star means how many elements are there? 6 elements are there. So you have to take from what? I equals to 1 to 6.
Yes, ma'am.
Right? And see here. Here in this case, in all the cases in middle I am getting 1, but see here in this particular case, at last, in this case at last I am getting 1, in this case at last I am getting 1. Then I can say that this becomes a primitive root. Clear? So in your logic, you have to write in that way a raised to I mode that is 1. But at that time, also you have to check this condition. At last, I want 1. In between, if 1 is there, then you have to break the loop. What is what I'm trying to say, everyone? So it becomes a primitive root. Is it clear, everyone? Please select. Okay. Only Priyanka is answering me. What about others? Okay. So listen, for algorithmic crypto system, in this way you have to find the primitive roots. So in this particular case you can say that 3 and 7 are the primitive roots, so this logic you have to implement. Okay, so first of all your task is you have to find the primitive roots. So in this case I am getting the two primitive roots, 3 and 7. So you can do one thing, because in algorithmic crypto system see here the two primitive roots, so you can store in some array or something, right? Or you can return the first primitive root. You can also do in that way, because I want any one primitive root for my algorithmic crypto system. So either you can store in array, or you can choose anyone. You can return the first whatever the first primitive root that you are writing. You can return. Okay, so in that way you can think about the logic. What you are writing. Okay, so now in this way you are get primitive root. So now once you get the primitive root, now see here. Now then, what is your next task? Your next task is, now for algorithm system, you have to do the key generation part. So now see here in this. So what I'm doing. So all of you know that let's say, see, actually basically what is your flow? So, flow in today's lab, what is your flow? First of all, you have to select any large prime number. Okay. So once you select any large prime number, so after that, what you have to do? So now see the next step of key generation, that is select even the primitive root of the group ZP star. So now see here right now, for which value of P you are getting this 3 and 7, everyone. See here. See, A raised to I mod 10, where P is what? Hello. So that for Zn star you are getting 1379. Okay. Now see your flow, everyone. First of all, enter some value by the user. Let's say the user entered equals to 10. Now after that, what you have to do? So for Zn star, okay, for Zn star, first you have to find the primitive roots. Okay, so you have to write the logic of primitive roots. Now all of you clear how to find the primitive roots. Now once you get the primitive roots, okay, so you can do the one thing here in Zn star. You are getting the two primitive roots, 3 and 7. So you can store in some array, or you can do one thing, return any of the primitive root. Okay, so that logic you have to write. Now select any of the primitive root from Zn7 star. Sorry, Zn star. You can take any primitive root. Now, once you get the primitive root, now then after what is the next logic? What you have to do? Select D to be a member of the group. So from this group ZT star, you have to select any D, right? Where the condition here I have given, that is 1 less than equals to D less than equals to P minus 2. So in your case, I have taken P, that is 10. So 10 minus 2, that is 8. So between this two value, any of the D you can choose. Okay. Now, once it is done, now then after you, the next step of key generation, that is E2 equals to E1 raised to D mod n. Mod. So all of you know that for this, which function you have to implement, can anyone write down in the chat window? Already that is this type of call. So can you write down in the chat window? Just square and multiply. So prime number, see, I have given you see wrong value that I have given, but see, simply in that way you have to do, right? Any prime number, there is also one trick for checking whether it's a that prime number or whether the primitive roots are find or not, right? There is another way that already that I have explained in your class. So if you want, Priyank, see just one number that I told you, but see, if you want to check whether the primitive roots are possible or not, so that part also I have explained in your class, right? That 2 4p raised to t, 2p raised to t, right? That concept already I have explained. I have also shared this PDF, so please refer to the manual. So from that you can get whether any number you are entering, whether the primitive roots are possible or not. So by using that formula, you can also check that thing. And if the primitive roots are possible, then you can find the primitive roots, right? Right? Okay, so you can check in that way also. Now see, here for that this function that already you have implemented, that is square and multiply. With the help of that, you get this value. Okay, so now the two keys are generated: public key and private key. Right, in every scenario, in this scenario, you have to assume the allies want to send some message to a Bob. So right now, the Bob perform the key generation, right? So now when Bob perform the key generation step, so at the end, Bob get the two key, public key and private key, right? So now so here you have to remember in Algama crypto system, the public key is E1, E2, and P, and this is the private key. Okay, so E1 and E2, that is the P, that is the public key. So now once the Bob generates the two key, public key and private key. So now then after what the allies will do? So allies have some plain text number, and with the help now Bob, what the Bob will do? Bob sends the public key to our allies. So allies have the plain text number, and with the help of this public key, right? Now what the allies will do? Encrypt the message, right? All of you know that. So in encryption part, what you have to do everyone? So this portion you have to implement C equals to the cybertext. That is 7 equals to even raised to number p. And remember that again the R is a random number that you have to choose from which group ZP star. From this ZP star and how to take in your logic. Okay, and after that, all of you know that the square and multiply method how to Now that is C2 equals to E raised to R mod P. So basically what you have to do, so all of you know that first you have to calculate E2 raised to R mod P. Now what is, right, whatever the first E2 raised to R mod P, all of you know that for square and multiply method is used. Whatever the value that you are getting, that is multiply with M, right? And again, whatever the answer that you are getting, you have to perform the mod P. And in that way you are getting this ciphertext C2. So all of you clear how to get this C1 and C2 ciphertext? Please reply everyone. Is it clear to you all? Right? So in this way you have to calculate C1 and C2. So now here you can say that now the allies have the two ciphertext C1 and C2. Right? Now once allies get the ciphertext C1 and C2, then after what the allies will do, the allies send this ciphertext C1 and C2, this encrypted text to a Bob. Right now, what the Bob will do? So Bob have a private key D. So with the help of this private key, now the Bob have a ciphertext, and with the help of the private key, Bob decrypt the message, or Bob decrypt it, and finally the Bob get N. So now see, all of you know this equation for decryption. M equals to C2 multiplied by C1 raised to D inverse mod P. So now see, in your implementation, what you have to do, I tell you, first of all, you have to calculate C1 raised to D mod P. Okay, C1 raised to D mod P by using a square and multiply method. Now, whatever the answer, C1 raised to D mod P, by applying the square and multiply method, whatever the answer you are getting, now you have to perform what? So, whatever the value you are getting, you have to perform the inverse with respect to mod P. Okay, so now all of you know the multiplicative inverse, all of you have that function, right? So first you have to calculate the square and multiply. So C1 raised to D mod P. So first apply square and multiply. Once you get the square and multiply, whatever the answer you are getting, now then after you have to apply the inverse with respect to mod P. So again you have that function multiplicative inverse that already that in first or second lab that you have implemented, and after that whatever the answer you are getting after the multiplicative inverse, now you have to multiply with C2, and then again you have to perform the mod P, and finally you get N. So all of you clear what you have to do? Is it clear to you all? So see, again I repeat this concept, everyone. See, again, just quickly, initially you have to take, initially you take the small prime number, and then after later try for large number. So first of all, take any prime number. Now then after, what you have to do? So whatever the number you are taking, so whatever the number you are taking, right, you have to perform what ZP star. For that, first of all you have to calculate the primitive root, and all of you know that from for primitive root, the two concepts that I have explained, cyclic generated, and another that is a raised to I mod n, that in your theory portion I have explained. So now the second one, it's easy. So that you have to try a raised to I mod n, a raised to I mod p, whatever the p value is, you have to calculate, and that what you have to check a raised to I mod n, that is one, as well as you have to check at last if you get in the last column if you get one, right? So now that is your primitive root. If in between the middle if you are getting a one, then you have to break the root. In this way you get the primitive root. So let's say two or more primitive root you are getting, then any of the primitive root that you have to take. Okay, now then after you have to find the, you have to take select D, right, that is a member of this ZP star group. Okay, and then after the next step is E2 equals to even raised to D mod P, that means square and multiply that you have to use, right? And so finally, this is the key generation portion. From that you are getting public key and private key, right? Once you get public key and private key, so now all of you know that after that you have to implement the encryption portion. In encryption portion, so you have to ask the user to enter some plain text, right? Now then after, how to find the C1 and C2? So what you have to do? So E1 raised to R mod P, so that means square and multiply method you have to apply. So what you get? C1. Now here in this method, first you have to calculate E2 raised to R mod P by using the what, square and multiply. Whatever the answer you are getting, multiply by M you have to do, and then finally you have to perform the P. So what you get? C2. So in this way, in this way you are getting two ciphertexts. And once you get the ciphertext, After that, how to perform the decryption? So in that, you have to remember that first you have to calculate C mod to D mod P by using a square and multiply. Once you get whatever the answer by using square and multiply, whatever the answer you are getting, you have to find the inverse by using a multiplicative inverse method with respect to mod P. And whatever the multiplicative inverse, right, whatever the answer you are getting, you have to multiply with C2, and again you have to perform the mod P. Then finally you get M. So all of you clear? Is there any doubt now in today's lab session? Right, I think all are clear. So your flow is, first of all, find out the primitive roots, right? Right, ask the user to enter some value of P, find out the primitive roots. Then for algorithm crypto system, perform the key generation, then encryption and decryption. So this is the flow of your today's lab. So all of you now implement your work. Okay, do your work, and if you have any doubt, then please ask me. Right, and also see once it is done, and then see one point that I have discussed in your class, that is see, I show you that thing, everyone. See this formula that I have explained. Right, so by using when you and ask when you ask the user enter the value of prime number, right, so initially by using this formula also you can check whether the primitive roots are possible or not. Right, if primitive roots are possible, then you can find the primitive roots, but later you can try this thing. Once the program is done, then after do that part, right? So it's good for you, because initially, see, if you are taking some number, but the primitive roots are not possible, so you are performing the whole implementation, and at the end you know that the primitive roots are not possible, right? So by using this rule, you can check whether the primitive roots are possible or not, and if the primitive roots are possible, then you can find the primitive roots, right? But this portion later you can try, everyone. Okay, so the material already that I have uploaded in your lecture in my folder, AMS folder. So you can refer to that material. Okay, is there any doubt? Please reply. Okay, so now do the implementation, everyone.
Okay, students, those who have understood what ma'am has taught and explained, you can continue implementation. In case if you have not understood, uh, I'm going to repeat all those things, right? And also inform others that I will be taking attendance now. So there are some students are absent, right? So in that case, I suggest you just inform them that they should join it the earliest. By the time I am going to repeat this, so there is a question by some student. Elliptic, Priyank, currently the lab topic is not elliptic curve material. Lab topic is algorithm crypto system. Okay, ma'am will do that as per our time. Others, those who have not understood, I'm going to repeat this. Okay, so lab objective, as ma'am already explained you, that there are 4 objectives in the lab. First objective is to write a function to create a primitive root for the given multiplicative group. Okay, this primitive root is used in the encryption and in key generation. Okay, and that is why the first task is to implement this primitive root. Second task is key generation. Third task is encryption. And fourth task is decryption. So these are the 4 tasks you are required to implement. Now, I will discuss the primitive route. This concept is very much, those who have already cleared, you can continue implementation. Those who have not cleared, for them I am going to repeat. So you can see another example. Ma'am has taken another example. I will be taking another example so that your fundamentals will be clear. So we have to find the primitive root for Z7 star for a operator multiplication. Okay. So which are the elements in Z7 star? So what is the meaning of Z7 star? What is the meaning of Z7 star? Can you type in the chat box? What is the difference between Z7 and Z7 star? If you can recollect your first sessional discussion. Okay. So I think you all are clear about it. So you don't need to understand it again. The elements of Z7 star are 1, 2, 3, 4, 5, and 6. Z7 means we have modulo 7. Those elements which are modulo 7. Z7 star, we get multiplicative inverse. Right? So this Euler's torsion function that you studied and also used in the RSA algorithm. So phi 7 is equals to 6. So if the number is prime, if phi of P is prime, then P minus 1. Okay, that you have studied. So it is satisfying that requirement. Now, to find the primitive root, these concepts of group and abelian group, I think it is clear to all of you. Okay, so I'm not going to discuss those parts. They are theoretical part we have already studied. So this primitive root finding method that we will see today. What we need is modulo 7. So our table that we are going to prepare, that is going to be modulo 7. Okay. So what we are doing in by finding the primitive root, we take a raised to I mod 7. Okay. So what is the value of I? I is total number of Z7 star. So we have to iterate it up to 6 times. 1, 2, 3, 4, 5, 6. Okay. And at that time, this iteration is for A values. A values are the values are going to be taken. So 1, 2, 3, 4, 5, 6 are the values. So we have to find A raised to I. So 1 raised to 1 is 1. 1 raised to 2 is 1. 1 raised to 3 is 1. 1 raised to 4 is 1. And 1 raised to 5 is 1. And 1 raised to 6 is also 1. But remember that what we have done is in the first row, 1 raised to 1 is 1 raised to 1 mod 7. 1 raised to 2 mod 7. 1 raised to 3 mod 7. 1 raised to 4 mod 7. That is why it is 1. Okay. Now we take 2. So 2 raised to 1, naturally it is 2. 2 raised to 2, 4. So 2 mod 7, 4 mod 7, 4. 2 raised to 3, that is 8. So now we have 8 mod 7, that is 1. Okay. Now 2 raised to 4, that is 16. So the remainder is 2. 2 raised to 5, that is 32, I think, uh, 32, and mode 7, that is, the result is 4. Okay. And 2:6, mod 7 is 1. Okay. So you can see that in first and second row, 1 appeared in the last column. Okay, for I equal to 6. But in both cases, 1 appeared earlier also. So this is the observation, remember, for calculation of primitive root. Okay. Now we consider third element, that is A3. So we take 3 raised to 1. Okay. 3 raised to 1 is 3. Okay. 3 raised to 1 is 3. 3 raised to 2, 9. Mod 7. Okay. 3 mod 7, 3. 9 mod 7 is 2. 3 raised to 3, 27. Right? 3 raised to 3 is 27. Mod 7. Mod 7. So the result is 6. We can write this. Okay. Now 3 raised to 4. 3 raised to 4 is 81. Right? 81. So 81 mod 7. So let us calculate it. Let me open my calculator, and you can also do this. A1 mod 7. So that results into 4. Okay. Now 3 raised to 5. Okay. 3. Let me change my calculator. 3 raised to 5. Okay. So 243. 243 mod 7. 243 mod 7. So that results into 243 mod 7 gives me 5. Okay. And last is 3 raised to 6 mod 7. This gives me 1. Now see, in this third row, what has happened is each element is unique. 3, 2, 6, 4, 5, and 1. And interestingly, all the elements of Z7 star, they are 1, 2, 3, 4, 5, 6, they are generated. See, you can see that it is generated, these elements are generated, same elements, the entire group elements are generated. That is why 3 is a generator. But condition is that this 1 should be the last one. So for I equal to 6, 1 is generated, and 1 did not appear earlier in this, any of this I. That is the condition which we have to apply while writing the program. Okay. So similarly, we can apply it for 4. So 4 raised to 1 mod 7, that is 4. Right? 4 raised to mod 1 mod 7, 4 raised to 2 mod 7, that is 2. Then 4 raised to 3 mod 7, it results into 1. So when you find 1 earlier, it means that you don't need to check the remaining elements, because it means that this value, A value, cannot be the generator or a primitive root. So the condition which we have to apply is that A raised to I mod 7, if it is 1, while I is not phi of P, right, or P minus 1, then break. Otherwise, continue. And if 1 is found, that is A raised to I. In case of 3, you can see A raised to I mod 7 is 1 for I equal to 6. That is phi of P. Okay. So this is the condition which we have to check. So it is not 1 earlier in this particular row, and it is 1 in all other rows. Now for phi, if we take, then we will have phi raised to 1 is 5, phi raised to 2 mod 7 is 4, phi raised to 3 mod 7 is 6, phi raised to uh, phi raised to 3 mod 7 is 6, phi raised to 4 mod 7, that results into 2, phi raised to 5 mod 7 results into 3, and finally phi raised to 6 mod 7 results into 1. So we have found another row in which all elements of Z7 star are generated: 5, 4, 6, 2, 3, 1. They may be in any order, but ensure that the last iteration results into 1. So this is our condition. Okay. So if you look at these two rows, we have generators or primitive roots. For 6, we will have 6 raised to 1 is 6, mod 7 is 6. Now 6 raised to 6, 36, mod 7 is 1. Okay. So we have found that it is 1. That means the remaining elements are not required to be checked. We can fill the table. They are going to be the repetition of all what we have found. But programmatically, we don't have to find it. Okay. So basically what we have is order. So order of 1 is 1. Order of 1 is total number of element. Okay. Order is total number of elements. So order of 1 is 1. Only one element is there. Order of 2 is 3. 2, 4, and 1. They are repeated. Okay. Order of 3 is 6. Order of 4 is 3. Order of 5 is 6. Order of 6 is 2. Right. So 3 and 5 are primitive roots or generator of for the group. So all group elements are generated with this primitive roots. 3 and 5 are the primitive roots. Okay. Is that clear to all of you? Any doubt in this primitive root calculation? Any doubts? Then we move to the second part. What if there are 3 primitive roots? What if there are 3 primitive roots? So we have to find all primitive roots. What was the problem? Find the primitive roots for group. We are only doing finding the primitive root. Now we are moving to the next part, that is key generation. Okay. Now let us discuss this key generation part. Okay. So this key generation part, the first step is, this first step is very important, and that you have also applied also, that you have to select P. and it should be very large prime number. Okay, for your program, you may start with 7 for testing your logic, but for after that, you have to take some large value. Now, second step is select E1. Okay, E1 you have to select. E1 is primitive root of the group. So what was the group? ZP, the prime number which you have selected, for which you have is and we have to apply it for multiplication. Okay. Okay. So this is our second step. So select one primitive root of the group E1. Third step is select B to be a member of the group E equal to, so from the same group, okay, same group, select a member such that it should be from 1 to 1 lesser equal to D lesser equal to E minus 2. So P is 7. Okay, in our example, P is 7. In our example, P is 7. Okay. So between 1 and 5, so usually you should avoid 1 and so boundary element you should avoid. That is by practice you can explain that 1 and 5 they should be avoided. Okay, so 2, 3, 4 you can take for the value of D. Okay, fourth step is take E2. Now second E2. So this is another member or element which we will be using for key generation, such that E1, okay, the primitive root which we have taken, for which E1 raised to D. D is, what is D? D is member of the group. Okay, E1 raised to D mod E. So E2 is E1 raised to D mod P. So we take a public key, that is, what we have done is we have taken one primitive root, we have taken one group member, and then we have calculated E2. So these three are actually public. Okay, these three are public. E1, E2, and D. These three values are public. Okay, these three values are public. And sorry, not D. D is actually private. D is private. D. Okay. D is private, and it should be with Bob. Okay. So this is our fifth step, and private key is is equal to D. Okay, so key generation part returns public key and private key. Now public key is generated by Bob and private key is kept by Bob. Public key is given to Alice. So with the help of public key, Alice will perform the encryption. That encrypted text will go to Bob, and with the help of private key, Bob will be able to perform decryption. So let us consider now encryption. What we are supposed to perform in the encryption. I think it is clear to all of you, those who are listening. Okay, key generation is over. All right, so let me explain encryption part. User Antri, are you getting? Are you able to understand? Have you understood this key generation part? Your doubts are clear? Okay, we are selecting one primitive root. We are selecting D, which is a member of the group. And then we are calculating E2. So E1, E2, and D. These three are taken from the group. Now E1 and E2 and P are public and D is private. Okay, the member of the group is private. It is kept by the Bob. Now we consider, now we perform this encryption part. Encryption, what we have to perform? Encryption, we have a message. Okay, so like RSA, what we have done in RSA, so algorithmal encryption, we have plain text. So we have one number. We are going to have one number. And with the help of public key, we will perform the encryption. So this entire public key and the plain text that we have. So what we have to do in the encryption part? Encryption part actually generates two ciphertext. Okay. Remember, this is different kind of algorithm in which there are two ciphertexts are generated. First ciphertext C1 is E1 raised to R. Okay, E1. Maybe I can enlarge it for your better reading. Okay, E1 raised to R. Okay, E1 raised to R. Mod P. E1 raised to R mod P. And this R is some random number. R is a random number. Okay. With the help of some R, we generate this C1, E1 raised to R mod P. R is a random number, but this random number is from group. Okay. So the group Z, the group G, ZP star, from the same, one of the member is randomly taken. And with that, with the help of that, we generate C1. Okay, C1 is one ciphertext, and that is going to be used for decryption purpose. There is another ciphertext which is going to be generated, that is C2, and C2 is equals to E2 raised to R into M. E2 raised to R into M mod P. This is our ciphertext. C2 is actually our ciphertext, but for decryption purpose we will need both C1 and C2. Okay, so that you have to understand. So how to implement this? The implementation of this key generation and uh, encryption algorithm requires e raised to x raised to I, okay, or a raised to x mod m. That algorithm, square and multiply algorithm, it was discussed during earlier lab. Okay, so the same algorithm you have to use for this calculation. RSA function for computation purpose can be used here. So this becomes very easy. So challenging part is primitive root and key generation, because the remaining are actually easy. So let us see now the decryption part. Elgamal decryption. So in decryption, what we are sending, the Alice has generated C1, C2. So we are sending C1 and C2. Okay, we are going to send C1 and C2. We are going to send C1 and C2. And we are also going to use D and P. See, once C1 and C2 is received by Bob, D already Bob has. So that is a private key. Okay. So Bob will be able to perform decryption. So with the help of these four values, Bob will perform decryption. So how to perform decryption? It is comparatively simple, straightforward. M is equals to C2 into C1 raised to D, C1 raised to D, okay, C1 raised to D, and its inverse. We will take its inverse, okay, multiplicative inverse. We will not only take inverse, we will take multiplicative inverse. And that is with the same concept. C1 raised to D you can calculate, and then you find its inverse. Okay. And then you take mod P. So you perform this mod P operation on three times, like C2 mod P, C1 raised to D mod P and its inverse, and then C2 multiplied by C1 raised to D mod inverse, and its value multiplication results into mod P. So three times you apply mod P operation. Okay, so is this clear to all of you? Those who understood, those who joined late or little bit late, understood? Any question related to this? Yes? Any question about the implementation? I think it is clear now. All right, let me take an attendance of yours. Okay. Yes, user. Understood everything? Very good. So if you have understood, will you be able to now write program for that? Okay. Others also, I believe that others are also implementing. In case of doubt, you can ask. Ma'am and I am both are available. You can ask us.
Hello, everyone. Hello. Uh, Hello, those who have not submitted lab, today is the last date for submission. So please submit it before 5:30. Is there any doubt, everyone? Primitive roots. Is there any doubt, everyone? If you are in doubt, then please a- ask me.
Yes, any update? Anybody has performed anything? Would you like to show primitive root generators? Anybody has implemented generator function? Anyone has implemented generator function? Am I audible? Have you implemented generator function? Priyank, user, user, have you implemented anything? Okay. Okay, Priyank, are you getting the output? Okay. Are you, what are you doing currently? Key generation?
Priyank, can you share your screen? Can you show us the primitive roots, Priyank? Can you show us the output of primitive roots? If it is possible, please. And listen, everyone, please try to communicate with us so we can understand. Please write down in the chat window how many students have finished the primitive roots.
Hello, ma'am. Is it visible?
Yes, your screen is visible.
Yes, ma'am. Here in this code, I have completed primitive root and stored into a vector of primitive root. So I will show you how it works. First, I need to enter the any prime number. So let I enter 7. Uh, for that, primitive root is 3 and 5. And public key and private key is represented.
Okay.
And then
So,
yes,
okay. Tell me.
See, this public key, private key is key generation part. So that is also done, you are saying. Okay.
and it is for the index. We
So,
need to
so in key generation, you have used 3, 2, and 7. Okay. Okay.
set. Then I enter the plain text. Uh, the decryption part is left, but that encryption part is done. The ciphertext is 3 and 6, which is generated using that R, which is plain text.
Okay, Priyank, good try. What about the other students? See how many students have implemented up to primitive roots. So please write down in the chat window, and everyone please communicate it, with us.
Type in a chat
See,
box if you have implemented primitive root code.
Birva, is it done?
Okay. Okay, good. Others, please type what is your status. Type your status, what you have done, how much it is finished. Each one of you type in a chat box. We want to see from response from each one of you.
Okay, good. Yash, Keval, Diva. And listen, everyone. Today is the last date for submission, right? So before 5:30, you have to submit. Okay, I have given you a deadline. So before the 5:30, you have to submit, everyone. Okay, Prince, no problem. See, once the whole primitive roots, key generation, encryption, and decryption is done, then later, if the time is remaining, you can try for that but equation P raised to T2 into P raised to T. See, basically, it's see, if you are taking any number and then later you find that the primitive roots are not possible, right? So these equations, see, by using this formula, you can check whether the primitive roots are possible or not. And if it is possible, then check, then try for primitive roots. So no problem, Prince. Once it is done, and if the time is remaining, then you can try for that. Keval, okay, whole program is done. So share your screen, Keval.
Hello, ma'am. Is it visible?
Yes, Keval, is it
Mm.
it's
Yes,
visible?
yes, ma'am. Let me show you the output. First, it is asking for the what is the prime number. So I have also check with this primality test using the Miller-Rabin. Let's say I'm not entering the prime number. Then
Keval, sorry for
yes,
interrupt you.
yes, ma'am.
Please, can you little bit zoom
Ma'am.
somewhat? Again, please, somewhat.
Now.
Yes. Now it's visible.
Thank you. Here I have the test using this primality testing a Miller-Rabin algorithm that whether the enter number is a prime number or not. So that is also I'm verifying it. Now I'm entering the prime number, that is it. Let's say 11. Then here I'm asking for the message that the user want to send to the receiver. Let's say message is a 7, and here the on the decrypted side we also got the 7. And here I'm printing the values of the elements of Z star, primitive roots, then value of E1, E2, D, R, ciphertext is this one, and this is the decrypted text.
Okay, good. Now, can you show your code and how
Yes, ma'am.
exactly it works?
Yes, ma'am. Just a minute. Okay. Uh, First of all, ma'am, here in this main, I am scanning for this prime number and checking whether it is successfully passed the primality test using the Miller-Rabin. Then I am scanning, expecting the message from the user, then calling this Algamal crypto system. And in the Algamal crypto system, the key generation part is starting. Here I am finding this Z star, then printing the value of this Z star. Then here I am finding the primitive roots. Then take the E1, that is the primitive roots, and here I have designed in such a way that it's written all the primitive vector, means the array of the primitive roots. So I am
Okay,
just taking one of
Keval,
yes,
for primitive roots, how you have implemented?
yes, ma'am. It is the function for the primitive root. So here I'm using this table method, ma'am. This one. Let me this one. Just a minute. This method I'm using, ma'am.
Okay,
And here it is the code of this. Square and multiply method is also used.
okay, yes.
Then and once we have this primitive root, I am taking the value of E1. Then I am taking the any random value between the range 1 less than 1 to P minus 2. Then I'm printing value of D. Then I'm generating the E2, that is the power E1 raised to D mode prime, that is using the square and multiply. Then I'm calling the encryption function. Now in encryption function, I'm also generating the R, that is a random number from the any element of this Z star. Then I'm generating C1 and C2 here, and I'm pushing into the one vector that is named as result, and I'm returning that vector and getting that vector here on the Algol crypto system function. Once encryption is done, I'm calling the description function. In decryption function, I'm just whatever it is C1 power D, then I'm finding multiplicator and inverse, and this is the formula to calculate decrypted text, and I'm returning just decrypted text.
Okay. See here you use C1 power D. In that case, also you can use the square and multiply method. Okay, Keval?
Yes, ma'am. Okay,
Okay,
let
you
me
can
try.
also do that square and multiply method. See,
Okay, ma'am,
don't
I
use
will try.
direct function. In each and every case, you have to use square and multiply.
Okay, ma'am.
And also you have to perform the mode. It is in the range.
Yes, ma'am. Yes.
See, Prince, you are correct. See, Keval, in this, you have taken the very small number. But see, if you take a very large number, then you have to take mode operation also. Because right now you have not taken mode. Because I told you that first you perform square and multiply
Yes, ma'am.
mode P. Then after in again whatever the number you are getting, you have to perform the then inverse mode P, and then again you have to multiply with and then again mode you have to perform.
Okay,
So
ma'am. I
that
will
part
try.
you have not done because yes, you Prince, you are correct. So the cable that part is remaining. The
Okay,
mode
ma'am.
each and every time you have to perform the mode.
Okay, ma'am.
Otherwise, see very means nicely you have implemented.
Yes.
Okay, good
Thank you,
try,
ma'am.
Keval.
Thank you.
Okay, Prince, is it done? Prince, can you unmute yourself? Prince, what is your question? Okay, no problem. Your question is if we enter the M is larger than P, then it will take, okay, M is larger than P. So see, normally you have to take the, according to that, right now you have to take the M value. Okay. And first of all, try it. Then after later, hello?
Yeah, one point I would like to inform you that in the beginning, I told you that P is supposed to be a very large. Okay, P is supposed to be a large. So M being larger than P is actually a rare situation. Okay, M is your message, right? And P is a prime number. You are saying. Prince, are you able to understand? P is prime number you are referring, and all of you. So that is what I am telling you that P value prime number is supposed to be very large for encryption. Okay, and all of you have to use this long integer data type. So that for 7 it is working for normal integer data type. But your program should be tested for a very large integer. So you have to find out a large integer, large prime number for which this program is working. So you should not satisfy yourself only for 7. 7 is one result, but you should, once it is done, logically it is done, right? So you have to test it for large prime number.
Okay, I think another student have finished the program, roll number 7. You are on 3. So can you share your screen? I want answer from everyone, right? So
Hello, ma'am.
yes, your
Is it
screen is
visible?
visible. Yes,
Yes, ma'am.
a little bit low. See, Your fonts are very small.
Is it visible now?
Yes, yes, now it's visible.
See, if we enter the prime number, say 11, and from range 0 to 10, if we enter any text, then it will give the output. Even it will give output if there is a large prime number.
Okay. How you have implemented?
First, I took the prime number and I have calculated P star and I am calculating the limit here. And
Okay.
then I'm selecting the D and selecting U. And then I'm generating the public and private key and then doing here an encryption and decryption. This is decryption and this is encryption.
So in each every case, you are using that square and multiply and
Yes,
multiplicative inverse. That
yes, 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 ma'am.
okay, okay, okay. Okay, fine.
And ma'am,
So
why?
you're using Python, right?
Yes, sir. And ma'am,
What is your question?
if we enter a non-prime number, then also it is working. Why is that so?
For non-prime, it is working.
Yes. See,
See, you have to test whether first, if it is, see, you are not checking whether it is a prime number or not.
yes,
Right? Your first, when you are giving input, if it is not a prime number, it should not accept it. Right? The program should not accept it. So that
yes,
is the logical condition you have to put.
yes, sir, that's true, but why is it working for non-prime number?
Working means it is generating result, but whether it is giving you correct decryption,
Yes, sir.
where what is the encryption value?
Let me print the encryption. Encryption is this, and decryption is also this.
Uh, See,
Enter any
here
other value? Enter any other value? Non-prime?
Non-prime. See.
No. Enter the large prime number. You are taking
Large prime number.
change that number. Instead of 115, you can take some other number.
Let me take value and yes, sir. Now
Okay.
now what?
Now you encrypt. Encrypt. No, what I'm saying is prime number is working,
Yes.
but non-prime another number.
Non-prime another number. Means
Yes.
15. Is it okay?
Yeah, you can take any other number
Okay.
for
Okay.
key. For
This is encryption and this is decryption.
no, I am saying instead of 7919, you take some non-prime number.
see, 3522, it's a two ciphertext. 35 is one and 322 is another.
No, it's one thing.
But see, here just wait. In encryption, the two ciphertexts are there. Where two
Yes,
cycles
but
are generated?
I have printed only one. If I
Okay,
like
okay.
this, seven, this is first and this.
Okay. But see, right now, see, I can tell you ki why it is showing this way. But see, basically, the purpose of this algorithm crypto system, right? That is, whenever you take any number, let's say, right? So one particular, like, you know, that 2 4 p raised to 3 2 into p raised to 3, that type of form that I have explained. So by using that, first of all, you have to check whether for this particular number, if it satisfies this condition, then this is a shortcut trick. If it satisfies this number, then you can say that it's a, because in that one point is that it check whether your number is a prime or not.
So
Okay, so
only
first of
that
all, you have to,
condition is left to check.
yeah, but see, the condition is there, your number must be a prime number, then you can check for that condition, right? So
Yeah.
basically, whenever, for algorithm crypto system, whenever you enter any number, right? So if you are, whether you are using this formula, see, basically, why we are using that formula, so that is useful to check whether the if that condition is satisfied, then the primitive roots are possible. That already that I have explained in your class. Yes or
Mhm.
no?
Yes.
Yes or no? Right.
Yes.
But see, first of all, you have to check your number must be a prime number, because if you are using that formula, then in that case also your number must be prime.
Okay. Else
Got
is
it?
fine.
See, basically in algorithm it must be a prime number, and see, normally in asymmetric crypto system, we are working with the prime numbers, right? And that's why in each and every case we are checking whether it's a prime number or not. So always you have to check whether it's a prime number or not, and then after you have to work on.
Yes. Only that condition is left. I will do it.
Yes, so you have to check that thing. Okay.
Yeah, sure.
Okay,
Okay.
and once your number is prime, so you can also, one condition that I have explained in your class, that is whether the primitive roots are possible or not. Right. So
Okay.
what happened if your number is not, if this condition is not satisfied, and let's say if you entering the 20 number, so
Mhm.
obviously you know that it's not a prime number, right? So if you are checking this condition, then directly by using that you can say that the primitive roots are not possible, because when the primitive roots are possible, if it's a prime, then the primitive roots are possible, you know that,
Yeah. Okay.
right? So you can also check that condition also.
Okay. Okay.
Clear?
Yes.
Okay.